So we finished yesterday with the conjugates with the square roots inside there, and one of those on that worksheet I passed out has a square root on there, so that one should definitely be doable. So some complex fractions. So you're really doing nothing more than just simplifying this out, but you really have to be careful on the math here. There's just a lot going on. So for this first one, you need to get common denominators here. So my common denominator is always the product of all the individual denominators. So I have an x plus 4 and I have a 4. So I sort of need to cross multiply those out. So we multiply by what I call well-chosen ones. So since this fraction right here is missing this x plus 4, I multiply by x plus 4 over x plus 4. And then since this fraction is missing the 4, I multiply by 4 over 4. So I'm really just multiplying by 1, but it's a well-chosen one in order to make the same denominator here. So I'm going to work this off over here in this space. So then 4 times 1, of course, is just 4. Minus, now it's minus 1 times this quantity, so please make sure you distribute that through the parentheses. And of course, we're still solving the limit as x approaches 0. And this is over now my common denominator of 4 times x plus 4 and 4 times x plus 4. So that's my denominator, 4 times x plus 4. It just allows me to make this as one fraction. That's all I'm really doing here. But then as you see, this is still all divided by x. Now when I get here, I don't like this because I see a fraction divided by a single term. I like to make this a fraction. Make sure you pay note, where is the actual fraction bar? What actually splits the top from the bottom? So I always make it a longer bar, so it's right here. So I'm going to make the bottom a fraction too. So it's a fraction over a fraction, and then we know to multiply by the reciprocal here. So you're going to start seeing both answers, which is fine, but I'm just going to work it out over here. So I'm going to simplify the top out here. So this is equal to the limit as x approaches 0 of, so if I distribute this through, I get negative x, and I get 4 minus 4. So the 4's cancel. I'm just left with negative x over that same denominator, 4 times x plus 4, all over x over 1. Well, then you multiply by the reciprocal of that second fraction, and you see these x's are going to go away here. So now I'm left with the limit as x approaches 0. So the denominator completely cancels. So the numerator, forgot parentheses there, the x's cancel now, and I'm just left with negative 1 over 4 times the quantity x plus 4. Now I can plug the limit straight in. 0 plus 4 is 4. 4 times 4 is 16. Negative 116. Remember, you can drop the limit once you start evaluating that problem out. And then you can see the same thing with the 1 over 3 plus h minus a third all over h. You do the same thing. You get the common denominators first. Well, actually, first you plug it in, which I didn't even do in the first problem. You really should plug the limit in first. Make sure you get 0 over 0. Then you need to start manipulating this around. So you plug 0 in for h. I have 1/3 minus 1/3 all over 0, so that's 0 over 0. Then you start getting common denominators. So you would multiply the left fraction by 3 over 3. You multiply this fraction by 3 plus h over 3 plus h. So the first step we have here, it sort of combines that all into one move, and then they start distributing that through. But again, notice it's minus the quantity 3 plus h. And then from there, it's virtually the same problem. The constants cancel. You're left with the variable h. You flip the h over 1. They cancel. And you'll eventually get the answer. Which appears to be negative 1/9 for that problem. All right, let's turn to some trig here. So there's going to be a limit or two we've explored a little bit, but not a whole lot yet. But then we'll see the definitions down below. So suppose we want to take the limit as x approaches 0 of tangent of x divided by x. So first off, how can we rewrite tangent of x? What's tangent the same as? Sine over cosine. So we're going to have, this is equal to the limit as x approaches 0, sine of x over cosine of x, and this is all over x over 1. Fraction over fraction, we're going to multiply by the reciprocal here. So this is going to be equal to the limit as x approaches 0 sine x over x times cosine of x. So remember, one of our limit properties from yesterday, the product of the limits equals the limit of the product. So I can actually split this into two separate limits. So I'm going to work over here just so we have some more room. So because right now if I plug in 0, sine of 0 is 0, and that's going to kill off that x, or x is going to kill off the bottom, so I have 0 over 0 right now. So I've got to manipulate this somehow. So I have the limit as x approaches 0 I'm going to just group the sine x over x together, and then that's going to leave me with the limit as x approaches 0 of 1 over cosine of x. So this, does anybody remember what that first limit was equal to? Sine x over x as x approaches 0? We looked at it once this year, and then we did it a little bit last year. It's 1. And this limit right here, the limit is x approaches 0 of 1 over cosine of x. Well, cosine of 0 is also 1. So it's 1 times 1 over 1, which gives me a limit of 1. I think I told you a few days ago, we will prove this limit. On Monday, I plan on proving that one out. So it does require quite a bit of geometry to be able to prove that limit here. And then for the second one, how can I rewrite cotangent of x, and how can I rewrite cosecant of x? Yes, yeah, that's right. Yeah, that's good. So the second one, because cotangent of x is equal to cosine of x over sine of x, all over then cosecant's the reciprocal of sine x. So multiply by the reciprocal. So of course the bottom just cancels out of there. And even the signs just cancel. So I'm really just left with here the limit as x approaches 0 of cosine of x. What's cosine of 0? There's your answer. There we go. All right, so 1 minus cosine of x over x, provided the limit goes to 0, is equal to 0. Sine x over x is equal to 1. Sine of some coefficient of x, so sine of ax over x, is just that a value. And really, even if there's a coefficient in front of this, if it was a over bx, well, then your answer would just be a over b. So it's just the ratio of the coefficients a lot of times for these trig functions. And then finally, the limit as x approaches 0, sine of ax over sine of bx. Again, it's just the ratio of the coefficients a over b. Provided in all 4 of these cases, the limit must go to 0. If the limit goes to any other number, that is not a true statement. Because in all 4 cases, when you plug in 0, you always get 0 over 0. So that means there's something to do to the problem. to get it to work out. But if it was x approaches 2, well, then your answer is just sine of 2 over 2, which is some number. I don't know what it is, but it's some number. So we only have to manipulate it when it's 0 over 0. And this second one's really just an extension of the first one, because if you conjugate this top, sort of do those trig identities from last year, it should work out to get you that limit of 0. Anyone need that still up? All right, so let's see if we can evaluate these limits algebraically here. So for number 1, so we plug the limit straight in. Sine of 0 is 0, cosine of 0 is 1. So I have 0 times 1 up top, divide by 0. Well, of course, that's 0 over 0, so that doesn't do me a whole lot of good. How can I split this or rearrange this or do something to it in order to get this to not be 0 over 0? Split it. Sin x over x, that's one of our key limits here. So for 1, we take the limit as x approaches 0 of sine x over x multiplied by the limit as x approaches 0 of cosine of x. We just learned this limit's equal to 1. Cosine of 0, we've already seen that today. We know that's 1. So there's your answer, 1. 1 times 1. What about this second one? What can we do to the second problem here? So for number 2, just take sine squared of h and split it into sine h times sine h. I think off to the right I have room to do that 1 minus cosine squared. You'll get the same answer. It'll just require maybe an extra step or two to get there. Now what am I going to do from this step? Can I transform that into any of our properties that we just saw? Sine h over h. Yeah, who cares what the variable is? It could be sine x over x, sine theta over theta, sine h over h. Notice I'm splitting, so the limit comes twice now. Limit as h approaches 0, sine h over h, times the limit as h approaches 0 of just sine h. Well, we know this new limit is just 1 times the sine of 0, but we know that to be 0. So we get 0 there. So the other way you could have solved it, which I honestly didn't even think about, use a trig identity, 1 minus cosine squared of h over h. So this factors and then from here, isn't that one of our 4 identities? What did we say that limit was equal to? 0. So if I take this as it approaches 0, this turns out to be 0, and I evaluate the other limit, 1 plus cosine of h. Well, cosine of 0 is 1. 1 plus 1 is 2, but who cares? So I'm multiplying it by 0. So you basically show in another step or two, you get 0 times 2, which is equal to 0. So it works. I said maybe an extra step, but you're thinking on that problem. What do we think for number 3 without doing any work? 2, 4 over 2. Yep. I don't know if there's a fourth one or not. There's one below there. And they show a lot of work for these limits here. I don't really need to see that. If you see sine of 4x over 2x on a quiz or test, and you tell me it's 2, I'm fine with that inside there. College boards never asked to see work on a limit, because they don't ask you limits on FRQs unless it applies L'Hopital's rule, but we'll get there at the end of the year. So if there's a limit you have, you can just evaluate it straight away. Oh, this is a good one. Anybody remember the sum and angle formulas for sine and cosine? I don't expect you to. That's fine. So I don't think we remember the proof for it then, which we're not going to do. Remember, I told you there's very few proofs in this course. So cosine of alpha plus beta which you will never have to know. If that's on there, if it's ever on an assessment, I will give you that formula. Cos A cos B minus sine A sine B. Hopefully you at least remember seeing something like that last year. So that means I can expand out this cosine of pi plus x. So this is equal to the limit as x approaches 0 of cosine of A, which is pi, times cosine of x minus sine of alpha, which is sine of pi, times sine of x. I still have this minus cosine of pi all over x. Okay? And again, what I didn't show, I should have shown plugging the 0 in for x, because I have cosine of pi minus cosine of pi, which cancels to 0 all over 0. So it means I have to manipulate this somehow. And in this case, it's using the sum and difference formulas for sine and cosine. So this can simplify up quite nicely here. So what does this turn out to be? Just that cosine of pi times cosine of x. What's cosine of pi? Negative 1. So it's just negative cosine of x. Okay. Minus what's sine of pi? 0. So that kills off that whole term. Don't have to worry about that. And then it's minus again, what's cosine of pi? Negative 1, so it's minus negative 1. So this is plus 1 all over x. So what if we rewrite this? Is the limit as x goes to 0 of 1 minus cosine of x over x. It's one of our 4 limits. It's 0. I don't know. I'm not a fan of that step. I've seen some textbooks write the limit as cosine of x minus 1 over x is also equal to 0, so that's why they factor out that negative. Our textbook writes it the way above it, 1 minus cosine of x over x. But either way, the answer is still going to be 0, because 0 and negative 0, of course, is the same thing inside there. Any questions on that? Again, I will give you those formulas if there happens to ever be something like that. Very good. All right, piecewise functions here. So when we're looking at piecewise functions, you only have to look at the part of the function in which the limit's talking about. So the limit of f of x is x approaches 0 from the right, or the limit is x approaches 0 from the left, and then the limit is x approaches 0. So I know we did piecewise functions last year. Did Kwiatkowski, Stone, did you do piecewise functions last year as well? A little bit? Okay. Something else I'm going to show you here, and I didn't show my students this last year either. You can graph piecewise on the graphing calculator. I think it'll come in handy a lot when you're looking at limits and talking about continuity here. So in order to graph piecewise, I didn't show you this year, did I? Okay. As I showed the pre-calc students, not you yet. Okay. So all you need to do in order to graph a piecewise function, just type in your function. So I'm going to type in x plus 2 squared. Nothing fancy there. Now this is where it comes in handy. This is weird. You divide. So you hit the division key. I always open up a set of parentheses. And then x, you put in your restriction. X, and then you hit the less than symbol. Second math has that test icon right there. So option 5, and then type in 0. And then let's type in the other part. Since it's multiple terms, I'm going to group this in parentheses just so it doesn't goof it up. So it's negative square root of x, get out of there, plus 4, divided by, open up parentheses, type in your restriction. X, second test, greater than or equal to is option 4, and 0. and then we're going to zoom 4. And there's your graph. I might want that y a little bit higher. So maybe we'll go up to 8 should suffice here. And there's your piecewise function. So it stops that parabola right there at 0. It picks up that second graph right there. That should come in handy for limits. If you can't really tell what's going on here, okay, fine. Then you can zoom box around that point in question. So you literally just draw a box around what you want to zoom in on. And the calculator will. Okay, now I'm pretty convinced of what that limit's doing there. Okay. All right. So that's how you do it graphically. Now, we can do this algebraically too. So 0 from the right, I'm only concerned with this function right here because this is right of 0. So if I plug 0 into this function, what do I get? 4. 0 from the left, I'm only concerned with this function right here because that's for all values x less than 0. If I plug 0 in, what do we get? Still 4. The fact the limit from the left matches the limit from the right tells me the limit itself is equal to 4. Same answer. Take a minute to work on number 2 here. See what you can come up with. All right. Hopefully, oh, thought I unfroze that. There we go. Hopefully you came up with those 3